All right, so next up, we have Alan Nikora, who received his PhD in computer science from USC in 1998 under Dr. Barry Bay. Barry was one of the members of his committee. He started at JPL as a flight software developer for the Galileo mission in 1978, moved into software assurance research in 1991, and retired from JPL in 2020. I am so glad that you here and that you're going to share your work with us. I think it will be of relevance to everyone here.
Well, I'm looking forward to it. I'm glad to be here. It's going to be a little bit of a different presentation from the previous ones. The subject will be a little bit different. We're going to be looking at software defects and failures rather than software cost. And this is going to be more of a high-level overview of pretty much everything that I did during my career at JPL rather than one individual thing. So let me go ahead and see if I can share my screen here. Can you guys hear me all right?
Yes, perfectly.
Okay, good. So let's go ahead and share that screen. Okay, so I'm going to go ahead and share that, and I'm going to need to share my computer audio too. So hang on a second. Let's see, share computer sound. Yes, I'm gonna need to do that. Now we'll start the slideshow, and you guys can see this all right?
Yes.
All righty. So this is a slightly updated version of a talk I gave a few years ago to the other members of the software assurance and assurance research group. The idea was that the old people with gray beards would give talks about all of the stuff that they had done to the people who didn't have gray beards so that they could supposedly learn from us. And this is what I talked about, building tools for discovery. So here's how I got to where I wound up at retirement. I started out in Milwaukee here. I'm trying to get this arrow to work here. There we go. Started out, I enjoyed amateur astronomy. Tried to do it for real, wound up in engineering and applied science. Spend most of my time at JPL, and here's where I worked with some of the people who are here and with Barry in computer science, but instead of cost, I did software reliability, and then back to JPL again. So we'll start off from where I started out. This is where I started out. Got nice and cold there, and this photo was taken in July. Can imagine what it's like December. Yes. So it's nice and cold, but it's compensated for by wonderfully clear skies, which got me to wondering about this stuff. What makes all those lights? How did they get there? And how can I find out what how they work? So that led me to my interest in astronomy here. And well, if I'm going to learn, I'm going to want to listen to people who know. And at that time, there started to be a lot of information available. These are some of the books for the interested public that I was looking at that time. And right around the time that I started getting interested in these things, we were starting to go past Mars and into orbit around Mars in the late 60s. And here we were, this is when we first discovered pulsars and started trying to figure out what they were. So lots of interesting stuff to look at. And if I'm going to find out, well, I'm going to want to build tools to look around and see what I can see. First, learn from people who know. From if any of you have built your own telescopes, you're probably familiar with these two books. These are ones that I read and took what I learned um, to make my own. If anybody here has made their own telescope, you've probably learned to do the barrel dance. And what you start out doing is making a glass sandwich that's got what's going to become your mirror. And here's the tool on which you grind your mirror. And the grinding is done by a slurry of progressive refiner abrasives and water. So all that you got to do is move the mirror blank back and forth like that at the same time that you're walking around a barrel like this. And lo and behold, if you're careful and following the instructions, you can make yourself a nice telescope. And this is actually a photo that I took through the telescope that I made. And well, this is an example of what other people have been doing. I think this is one of Galileo's drawings here. So that got me wanting to be an astronomer. So I decided that I wanted to go to Caltech, and I got in. And here's where I spent a fair amount of my time the first couple of years. This is the old
The hell are
astronomy
you
building.
doing?
And if you look up here, this is a 1/10 scale replica of the Palomar telescope. They built an engineering model and installed it on top of this building. And I spent many nights doing observing on the top of that on the top of this building. Now at that time and still, Caltech was a great place to do astronomy. They had there were outstanding people there. Jesse Greenstein, for instance, discovered white dwarfs. Martin Schmidt and Wal Sargent figured out what quasars are. And well, Kip Thorne, who we now associate with the gravitational observatories. Great research facilities. At that time, there were the telescopes at Palomar and Solar Observatory, and now we have more of them, including the gravitational observatories. And at that time, even undergrads could get time at Mount Palomar. Well, the thing that was going on at that time, though, is this gives you sort of an idea of what kind of an astronomy student I was. Compare it to the other astronomy students. And between the capabilities of the other students and some of the more advanced physics classes, I decided that maybe it wasn't quite for me, but at least I could build tools. So I wound up in engineering and applied science and promptly went to JPL, where my very first job was working on the Galileo flight software for the command and data subsystem on board the spacecraft. So still building tools for discovery there. And here is an artist's Magellan mission, which used spare parts from Galileo. But when I was working on that, I started wondering, where do all of the defects in the software come from? During development and testing, we would discover defects in the software that I thought should not have been involved there in the first place. And that got me to wondering, what can we do about it? Now, I did take a brief intermission away from JPL, at which I became a software quality assurance engineer, and that got me interested even more in software defect management. We want to answer questions like, how many defects are we going to put into the software during development? How many can we prevent or remove before we send the software out to the customer? If I'm going too fast or skipping over stuff, by the way, please let me know. I've been through this material plenty of times, and since I know it, I figure everybody else knows it too. So my time at Ashton Tate got me even more interested in these two questions, and that got me involved in building another kind of tool for discovery, which is developing models for software reliability, in which we can use to discover what the behavior of our spacecraft is going to be once it's during test and once it's out in the field. So I came back to JPL, and at this point I started doing research in software reliability. There was a director's discretionary fund effort to look at software reliability modeling at that time. And what I looked at specifically was how to apply software reliability models to JPL missions effectively. There is a handbook that I wrote, over 30 years ago now. I don't know if it's still available, but what I learned went into these two recommended practices and standards. This AIAA recommended practice on software reliability, I think came out in 1992, and eventually became all the basis of all of the versions of this IEEE standard, which was last updated close to 10 years ago, I think, and it's due for another update. But this one is still a current standard, and it builds on, and it includes some of the work that I did, and as well as work that a lot of other of my colleagues did. So this is the first tool, if you will, that I built for discovering how the systems that we send out into the solar system are going to behave. And well, I was still doing what I wanted, pretty close to what I wanted to do in the first place. The intent of this tool was to be able to answer questions like that. Can I release the software now? And if I can, how much more testing time is it going to take me to reach the reliability goal that I've set? And what are the consequences if you don't have enough time to finish the testing? Now this is similar to the kind of stuff that that Bill Tabor talked about yesterday, and the models that were included in this tool were the ones that were available in the let's say in the early 1990s. And this was about this was the first Windows-based tool to include multiple models for different types of data. This particular tool is not available anymore. It was built to run in Windows, but there is a descendant called SFRAT, Software Failure Risk Analysis Tool. If you put that into your search engine, that will take you to the page on which you can download that particular tool. This was built by a colleague of mine, Lance Fiandella, at UMass Dartmouth, and some of his students and I. And it's written in R, so it's going to run on any platform. So that particular tool is being maintained, I believe, and it's available as in the public as an open source tool. Now, does anybody have any questions before I go on? I think I'm zipping through this stuff pretty quick here. So around this time, I was getting more involved in the research, but my background had been electrical engineering, so I thought that it was time to to um, uh, to become more knowledgeable about what I was doing. I liked what I was doing. How can I keep doing? So I made the decision to go back to school and learn from people who know um, more about the kind of stuff that I want to keep doing, look around and observe. This is when I met Barry. He was just getting onto the faculty at about that time. I think about 91 or 92, and I was fortunate enough to get him to agree to be a member of my committee. And if the things that I learned from him, I think were quite important in my being able to successfully complete the program. Um, although I had already figured out uh, the importance of getting good data, working with Barry showed me what you need to keep in mind when collecting your data. You need to know where it comes from. What does it mean? Do you think it means the same thing as what your customer think it means? And is what you're collecting going to be consistent with the goal that you have? So what I did here was develop a way of relating software defect content from uh, it's a simple technique that I developed. It's just an application of a birth and death model. You've got a fault insertion rate and the fault removal rate. Uh, um, discrete state continuous time, simple model, but getting the data was a much more critical and important thing. As Carol said a little bit earlier this morning, software data is probably some of the worst data that we have, and she wasn't kidding. Um, getting getting some of the information, such for example, the way that the structure of the code changes over time, but getting information about actual defects as opposed to failures, that gets to be a much more interesting proposition. And I won't go into the details here, but in order to get a model that produced reasonably good estimates, I had to develop a quantitative definition for what a software defect looks like. And and one of the things that you have to recognize in this case is that a single failure report might cover multiple defects. So that got to be interesting in a number of different ways. But but I was able to develop that model, and I had hoped to be able to put it into practice for the way that JPL did business. In And there was some partial success, but this complete model is not a in did not become a part of the way that the lab did business. And as far as software development and testing is concerned. Now, um, after finishing the dissertation, though, we can I kept looking at software failures, but in different ways. There's lots of variety in software failures, and they exhibit interesting behavior. And well, let's see. The recent tools are not quite as recent anymore because this has been a couple of years since I did this presentation. But there were the types of data that I gathered and analyzed were, what are the types of faults that we encounter in our space mission system software, and this includes both flight software and software on the ground, and what do the types of repairs and mitigations for that software look like. Now, one of the things that some colleagues I was working with and I thought about were, well, what what about various types of software defects? Can they It's likely that different types of defects are going to cause different types of failures. And can we categorize defects in a software system in a useful way so that we can see if this is the case or not. So some of you probably know Kishore Trivedi and his colleagues at Duke University. So we were looking at simple versus complex faults, which you may know as Bohr bugs and Mandel bugs. And the conjecture that we were looking at was that the faults in a thoroughly tested piece of operational software should I go through that? Whoops. Okay, well, I can't see the chat here, so let me.
You froze for just a little bit, but you're back. So
Oh, okay. All right. All right. Do I need to go through what borer bugs and mandelbugs are briefly, or do people know?
I think we were able to hear the gist of it. You were actually just getting towards the conjecture when you had frozen.
Oh, okay. All right. Yeah, if I drop out again, please let me know. I've noticed that my audio's been a little bit flaky sometimes. So we looked at the failure reports for a number of different um missions developed and managed by JPL. And interestingly, what we found is that the majority of our operational software defects appeared to be these simple, repeatable borer bugs rather than the more complex, often unreproducible mandelbugs. Interestingly enough, too, the simple defects seem to be associated with the more severe failure effects. Now, you're probably wondering how we determined uh, um, which failure reports corresponded to which type of defect, and it's a simple answer. We took the entire database of several thousand anomaly reports for these missions, and we had a couple of people read them independently of each other. And although it was arduous, it seemed to work pretty well. Um, there were not too many disagreements between the two readers. One of the readers was me, and any disagreements that we did have were pretty easily resolved. So simple way of determining defects, interesting results. What we found was we seemed to be getting stuck on the simple stuff. Now we also reasoned that different types of defects might be corrected in different ways. And is there anything that we can say about defect types and mitigation types, and trends in proportions of correction action types within missions, as well as from mission to mission? How am I doing on time?
You have about 15 minutes, but if we go a little late, that's okay.
Okay, well, I'm good. I think I'm about right where I should be. So let's take a look at software faults and software failures versus mitigations. And here's where the first sound effects ought to be coming in. Here we've got actual fixes. You can fix or patch the software, you can develop a workaround, or you can use it as it is in response to a failure. Or mitigations include reconfiguration, failover to a non-identical copy. We don't do this at JPL that I can recall. Not non-identical replicas are expensive to produce, and they're not quite that critical. Did you guys hear that doorbell, by the way?
I did, yes.
Okay, good. Yeah, so for borer bugs, uh, we usually wind up using either fault mitigation or one of these failure mitigations. If I remember properly, we tend to mitigate the faults more commonly than we do failures. Uh, bore bore bugs are bore bugs are nice and simple. They'll manifest the same way under identical circumstances, and it's um they'll reproduce the same behavior consistently. And once you've seen them, it's usually pretty straightforward to identify the defects that are associated with failures. Now, here on the other hand, you've got this thing that you can't tell quite what it is. This is your mandelbug. Under different conditions, it's going to manifest in different ways. Under what you think might be identical conditions, it might manifest in different ways too. And interestingly enough, even though they might be hard to reproduce, um, under test conditions, we found that a lot of them tend to be actually fixed, and mitigation techniques are used on the rest of them. And here is an option that you don't really have with the borer bugs, because of this property of mandelbugs, that under apparently identical conditions, they will manifest in a different way. So with mandelbugs, you can either retry or restart or reboot or fail over to an identical, and this type of failover is going to work, um, because it's likely that the usage profiles in this identical replica are not going to be the same as in the system in which as in the replica in which you just observed the failure. So that was a pretty interesting thing that we found. So most simple faults, you mitigate them with fixes. Um, the most common mitigation for the mandelbugs also appeared to be fixes. And this was interesting too. For the data we
Drop,
don't know. Sorry, yes, go ahead, please.
repeat the last point.
Oh, so for the failure data that we looked at, the more recent missions appeared to mitigate the complex faults with fixes more frequently than complex faults were fixed in earlier missions. That's kind of interesting. We don't know why that is. We the research effort ended just as we were getting to this point. One of the things that we thought might be possible is that the fault isolation and repair capabilities were not as good for the earlier missions as they were for the later ones. There has been time to develop better testing and development tools, but we couldn't determine it. We couldn't determine if that had an effect or not. That would be an interesting thing to look at for somebody else at this point. Now, what else did I wind up doing? I still wanted to understand better where defects come from, what do they look like, and what we can do. There's lots of information in JPL's problem failure report and incident surprise anomaly reporting systems, other problem reporting and tracking systems. there's natural language descriptions of the anomalies, the analyses, and verification that were done to confirm the behavior and corrective action. But as I said, it's not structured information. So how can we turn all of that information into something useful? Well, I tried looking at a couple of things, and they're made pop. I was able to do some semi-automated extraction of some useful information because um, we've got industrial strength techniques for doing this sort of things, and CPU cycles are cheap and plentiful. So I wound up learning something about machine learning and topic modeling here, and the machine learning, I used supervised machine learning. Um, I I I I used machine learning to see if it was possible to identify um timing and timing related defects from non-timing related defects using, and it turns out that that I was able to do able to develop a reasonably good model from the data in the failure reports. Topic modeling, we can think of that as the data cloud, the word.
You dropped out again.
And apply this technique
You
to
dropped out again.
so thank you. So the idea is that you apply this topping modeling technique to a set of documents, and this will tell you what is the most likely set of topics overall, and which topic or topics are associated with each individual document. So you can, so a topic, for example, will look kind of like a word cloud. Topic 2, whatever you decide to call topic 2, will have these words associated with it. And topic 7 will have, for example, these words associated with it. And what you'll be able to determine is which topic or topics are associated with each of these documents, and which is the most important topic or topics for each individual document. So I'm gonna skip explaining this little ornamentation thing here, but the thing that you can do with a topic model is you can take your set of anomaly reports and see which topic occurs the most frequently, and that will help you focus your any process improvement or corrective actions that you may need to do. And you can also see if your mix of topics is changing over time, and that will give you additional information on improving your corrective action process. Now, this as our systems become more complicated, it seems to be getting harder to distinguish between correct and incorrect behavior. You've got your non-deterministic behavior and fairly limited data availability in some cases, and it's getting much harder to completely specify the desired behavior, particularly if you have massively parallel computing, onboard autonomous science, which we are starting to look at, and autonomous fault detection and system health management and reconfiguration. So let's go to a couple of examples of what complexity looks like. So here we've got an audio equivalent of what our current and historical systems look like. You've got a nice simple specification here. It follows well-established rules of thematic and harmonic progression. The musical form has been around for a while, so you can look at the score and get a good idea of what the correct thing should sound like, as we just did. And if you only have a partial version of this, you can use those rules that we know to make a good guess at filling in what the rest of this is. And the thing is structured well enough that it would be easy to write out the equivalent of test cases. Here's what we're heading to. This is real. These don't correspond to that, of course. But the real score is close enough to this that you can see what's going on there. The rules are not nearly as well established for this kind of music. There's no well-defined set of structural rules, thematic progression, harmonic progression. It's not easy to look at this and determine if what's coming out is a correct representation of what's written down on the paper. So the questions become, how do we test systems that are more increasingly complicated? And how can we more effectively learn from our previous systems? How can we relate the failures and defects to our system design and specification? And here it gets interesting. How can we relate the user interaction to the system characteristics? And again, much of our potentially useful information is unstructured. Anomaly reports, higher level requirements. And the good news with this is that natural language processing techniques and analysis techniques, including machine learning and topic modeling, are capable enough to be used to be able to ingest and analyze this kind of data. So we've already been here. So this is a pretty good summary of what I did during my time at JPL. If you remember Cat's Cradle, one of the characters in the book makes this statement, and there were times I felt just like that. There's a lot of interesting stuff to look at in the world of defect and software fault analysis and management. And it's it was it was it it was all interesting and sometimes hard to focus on just the one thing. And sometimes it even
You dropped out again.
and if anybody have any questions, yes, please.
Repeat the summary.
Oh, right. Let me go back. So you may remember this little passage from A Cat's Cradle. This was pretty much the way that I feel about the time that I spent looking at this stuff at JPL. Lots of interesting things there, and it didn't matter what you looked at. There was always something interesting and useful to do, and sometimes it even made sense.
So, were you involved at all with Sunita Chilani and her?
Yeah, she was there. She was at USC at the same time I was.
Right. And she graduated a couple of years later.
Mm-hmm.
And then you do know about the model she produced.
Let's see, Coqualmo, right?
Right. Okay. Fine.
Yeah, sure.
Did you happen to provide data for that?
I think I might have provided some. That gets back to the point that Carol made earlier about software data not necessarily being very good. Some of the data that Sunita was asking for, I was able to provide some of it, and I don't remember details. I couldn't do much more than look at the request and say, well, gee, that would be useful. I don't know how to get that.
Okay, thank you. There's a query in the chat. It says, Alan, are you saying that systems are evolving to be so complex that eventually faults can be observed but not corrected?
That's some of it, and it may also be the case that defects may trigger a fault that you don't observe, that for which you can't tell it's a fault. You'll observe what the fault does, but might not necessarily know it's a failure.
One other interesting observation. Have you ever heard Michael Fagan talk about Fagan's inspections?
I haven't heard him speak. I've read his work though.
Well, one of the interesting things about the process that he goes through to get Fagan's inspections installed in an algorithm, in an organization, boy, how's that for my mixed up head today? Get it into an organization is that he goes in and pulls in a complex, have the participants in the training sessions literally bring in a piece of real code that's operational, ideally. And they split up into teams and they go through and do a Fagan's inspections of part of it after they've learned the technique. And they come back in, and in that very first
Oh,
session,
excuse me, Sam. I'm sorry. You dropped out.
no, this is Windsor Brown.
Oh, so sorry, Windsor.
That's okay.
You just dropped out.
Interesting. Okay.
Yeah. Like I said,
Anyway,
my audio is a little flaky
during,
sometimes.
during setting up the training for an organization, he requires upper management in the software hierarchy of management to be present. And one of the things, and they even participate in the inspection, even though they may not contribute much. But one of the things that happens is that invariably they will find the participants will find a defect in the code that they've been inspecting. This is operational code. And the reaction was from other people there, as these are discussed in an open forum, says, oh my gosh, that explains why this weird fault always kept appearing, but we never could repeat it.
I've heard that. And
well, I've seen it happen multiple times. Okay.
Yeah, but
and
back about 30 years ago, we actually started putting inspections in place at JPL. And when we were first getting them set up, we noticed things like that. You know, it wasn't necessarily in the code. It was in some of the higher level artifacts, but we were seeing some of the same sort of thing.
okay, well, thank you.
Thank you. Oh, and I see that Jim and also enjoyed 1, 2, 3 Infinity.
Yeah, keep listening.
And does anybody have any other questions? If not, I'll turn off my sharing and return to Julie. Well, to Anandi.
Thank you, Alan. That was a very interesting talk. I'm so glad you were able to share it with us.
Well, I'm glad I'm able to be here. Thanks for inviting me.
Definitely.